Alright, so this is going to be just a quick explanation of Ohm's law. So we could read the spec if we really wanted to. And I'm going to skip that basically. I've already read the spec. I know what I'm talking about. You've essentially got to be able to understand and apply this formula. And what I've found in the past is that students have no problem with applying the formula. They just don't really believe it. So I think it's worth spending a bit of time thinking about what all these terms mean. So I like this picture. This picture helps you understand what's going on. So voltage is like the push. It's the thing that's pushing the charges through the wire. Resistance is the thing that, as you can see, the lasso here is slowing down the current and is measured in ohms. So what we've got here is we've got the same formula, V equals IR, and voltage is doing the pushing. Current is the stuff that is flowing through the pipe, and resistance is the thing stopping the current from flowing. And these three terms are all related to each other. So I think an important thing to think about when you're thinking about Ohm's law is it is the definition of resistance, essentially. So I've got a straw here, and if I blow through this straw, if I blow as hard as I can, right, I can get a certain amount of air to go through that straw per second. We could think of the speed at which the air is going through the straw in litres per second, right? And that would be a bit like thinking about charges flowing as well. If when I'm blowing through the straw, I pinch it, it gets much harder, right? Now, if you wanted to know how hard it was, that'd be like asking what the resistance was. And we could measure that by looking at how red my face goes. So, right, that would work. Not very accurately, right? But another way of thinking about defining or explaining how hard it is to blow the air through, or the resistance, how big the resistance is by comparing how hard I'm blowing to how fast the air is moving. Or even, if I could say on a scale of 1 to 10, I was blowing at a 10 and the air was going through here at a 5, right? If I got another straw now and doubled them up and I blow at a 10, it's much easier to blow air through. So now when I'm blowing, I'm pushing at a 10 and the air is coming through at a 10, right? The resistance is lower. You could do 10 divided by 10, 10 for how hard I'm blowing and 10 for how fast the air is going, and you get 1. In the previous example, if I blow at the 10, I only get 5 coming through, and 10 divided by 5 is 2. So that would be a higher resistance. So this is one way of thinking about it, right? Let's draw it out. So one straw, when I blow with a 10, blow as hard as I can, 10 out of 10, right? And I'm getting a flow rate of just 5, maybe litres per second of air, right? And I could say 10 over 5 gave me a resistance for this straw of, what's 10 divided by 5? Is 2. So 2 red faces, right? That's my unit of resistance for straws. But when I did 2 straws, much easier to blow the air through. So 2 straws actually in parallel. I'll make them really bad drawing, but okay. So there's 2 straws, and I blew into both of them at the same time, and so I was pushing the air in with a force of 10, blowing down that with a force of 10, or a pressure of 10, however you want to think about it. And down each straw we were still getting 5 litres per second, right? Litres per second. But in total, that was 10 litres per second, right? And I could say 10 over 10, right? So 10 for the how hard I was blowing, and the 10 for the how fast the stuff was flowing, and I get 2 red faces of resistance, right? So that's one way of thinking about resistance. It's an analogy. It's a bit of a crazy analogy, but the idea is here is just to get comfortable with what the formulas mean, right? So if we wanted to do this in a circuit, we would do this. We'd have a cell. I'll just get this pen a bit thicker. We'd have a cell, right? useful thing to remember here, the big side is always the positive side. Bigger is better, apparently. Right? We put a resistor here. This is the symbol for a resistor. We are going to measure with an ammeter in series how much current is flowing. And then we use a voltmeter in parallel, and this leg asks the charges how much energy have you got, and this leg asks the charges how much energy have you got, and the voltmeter will display the difference, right? And then what we could do is we could say this is a one cell, 1 volt. We could make a table of voltage against current, right, and start messing around with it and recording our values. So I'm going to keep it really straightforward just to get the gist of the idea across without worrying about specifics and numbers. So if I tried 1 cell, I might get a small voltage and a small current. If I then went in and added another cell, keep them in the right orientation. So now I've doubled up the voltage has got bigger, the current would also get bigger, right? And then I add another cell. Okay, again, voltage has got bigger, current will get bigger, right? Just like if I was to blow harder, I'd get more air going through that straw. And if you was to put this on a graph, right? Now, normally we put the thing we're measuring, and here we're measuring the current and we're changing the voltage. We normally would put current on this side of the graph and voltage on this side of the graph. But just for this presentation and for this idea, I'm going to do it the other way around because it is convenient for something we're going to do a little bit later. So I'm going to put voltage here and current here, okay? And you can see small voltage would give you a small current, so you put a cross here, bigger and bigger, and you get your 3 plots and you get a straight line, right? For 1 resistor, right? Now, we're going to do the equivalent now of either double up the straws like this, make them extra long, which will make it harder to blow the air through, much harder when you've got a longer straw. If you don't believe me, you can try it. Or we can think of it as pinching the straw. So I'm going to change now. So these were my current values for just 1 resistance, right? And what I'm going to do is I'm going to double up. I'm going to get 2 resistors now and do the experiment again. Okay, so 2 resistors this time. So I'm going to be recording values for 2 resistors. Okay. So now we can imagine, again, I'm not going to redraw all these again, but we can imagine that we just have 1 cell to start with, right? And if we have just 1 cell, we'd expect to get a, for this 1 small voltage, we'd expect to get a current, but it would be smaller than prior. It'd be smaller than this one, right? It'd be smaller than this one. If you then added another cell, right? So, so we get another cell involved. Made a bit of a mess of that, oh well, right? So now we're thinking what it would be like if we had 2 cells. The current would still go up, but it wouldn't go up by as much. And if I add a 3rd cell, the current still goes up, but not by quite as much. So what's it going to look like on the graph? Well, this time, for the small voltage, I would get a smaller current. So it would correspond to, say, here. Now when I doubled up the voltage, last time we got that much current for this voltage, but we're getting less this time, right? Because it's a little bit smaller. And again, a little bit smaller, right? And what you end up with is a steeper line, right? Trying to draw a line of best fit there. You get told off in the exams if you do a messy one like that, right? And it is the steepness of this line, or the ratio of the voltage to the current, that determines or defines resistance, right? So when we had 2 resistors like this, which is really tough to get through, that's big resistance and it's a steep line, right? When we had 1 resistance, that was a small resistance, and it's a shallower line, right? And the right word to describe the steepness of a line is gradient. So you could go back to your math skills now and go, oh, well, I know how to calculate gradient, right? Gradient is change in y over change in x. And if we actually look at these terms, the terms we would be using would be the change in v divided by the change in I. So you would be doing, if I was to replace or substitute x and y, if I was to substitute this and this with the terms of the graph, I would be substituting them with v and I. So I'd have v over I. And then I'm telling you that the gradient is actually the resistance. So R is equal to V divided by I, which is what, if you rearrange it, if I multiply both sides by I can cancel here, and I've got backwards, but it's V equals IR, which is the formula we came to initially. Right? Oh, get to it. Right, so that is actually what this formula is all about. It's about defining resistance in terms of voltage and current. And I think that it's actually pretty important to be able to look at and understand what's going on the graph. Now, this graph, if I was to turn these cells around, so just rubble this out and say the cells were that way around before, but I want them this way around this time. Small side this side, big side this side, right? This time just making the current flow in the opposite direction. And on the graph we would represent that by a negative value for current, right? And you would get these lines continuing down like this, right? This looks like a hell of a mess. I'm just going to simplify it up here. So voltage and current would look something like this. You could have, and this would represent a big resistance, and this would represent a small resistance. Right, so now's the tricky bit. When I say it's tricky, it's not that bad. As I mentioned previously, we normally conventionally put current here and voltage here, because when we're normally plotting a graph, we're plotting the thing we are measuring on the y-axis. I mean, if you imagine after Christmas when I need to lose a little bit of weight, I plot a graph of my weight against time like this, and hopefully I see this happening, right? And that makes sense. So that's normally how scientists will interpret data. They'll put the thing they're interested in measuring on the y-axis. So if we did that, then it's like taking this graph and rotating it around that way, right? Just turning it around in a circle, okay? But basically it's going to look the same. The only difference is that this now represents the big resistance and this represents the small resistance. And you can't really, you could do the gradient of this graph and calculate the resistance, but you'd have to take the inverse of the gradient value you got, right? So if you did current over voltage, if you did 1 over that value, you would still get the resistance. Okay, so I think this video is really aimed at just giving you a better gist, a better feel for what Ohm's law is all about. Hopefully this picture means a bit more to you now. If you found this type of thing useful, I'm just playing around with my new camera and recording setup. So if you found this type of thing useful, maybe make a request and I can have a go at making some more videos like this. Thanks for watching.